So it turns out pretty much everyone we talk to is a runner. And I like to rub that into Ernest's face because he's not a runner.
No.
So let's just kick this off, right? And start by rubbing that in your face, Ernest.
Boy.
That's fine, but I'm willing to bet money I can bench press and squat more than both of you. So
You would probably win
I'm
that.
not a runner.
You probably
I think
can.
you'd win that.
Hi, everyone. I'm Jolie Hales.
And I'm Ernest De Leon.
And welcome to the Big Compute Podcast. Here we celebrate innovation in a world of virtually unlimited compute, and we do it one important story at a time. We talk about the stories behind scientists and engineers who are embracing the power of high-performance computing to better the lives of all of us.
From the products we use every day to the technology of tomorrow, computational engineering plays a direct role in making it all happen, whether people know it or not.
Hey, Ernest.
Yep.
So I've got another episode kickoff question for you.
These are always, I'm sure our listeners love these.
I can't tell how much sarcasm is in that statement.
It always sets up the mood.
Which is usually ridiculous, let's be honest.
I mean, yeah.
Okay, but I'm going to ask it anyway. Do you consider yourself a football fan? Meaning American football?
I'm not really a fan of any sports at all. However, I do watch things like the Super Bowl, the NBA championships, things like I'll watch the very end just to see, who wins. But aside from that, no.
So not a big sports guy.
No, as far as I'm concerned, it's essentially what the Romans were doing with the Colosseum as the empire burned around them.
Wow. That is quite the perspective on sports. I've never heard that before. All right. Well, then this episode might be kind of boring to you.
I'm sure it won't be boring, but it's just one of those where it's like, I have a finite amount of time in this world. And
Right.
the things I choose to do with it, sports is not one of them.
Yeah, so I feel you. I don't have time to really watch any sports at all either. I think it's just that phase of life. Maybe someday that time will open up again. But for me, when it comes to American football, I watched it a little bit when I was growing up. My parents and my grandparents would take me to like Utah State Aggie football games as a kid, which was kind of fun. But as far as the NFL goes, I never really got into football like I was into watching the NBA, actually. I was a big NBA fan growing up, though nowadays I don't really have time to watch. Big Jazz fan, actually. But as far as playing football, I mean, did you ever play football growing up?
Yes, I did play football growing up.
Okay, cool. The only time I played tackle football was in Powder Puff. Did you guys have Powder Puff in Texas? I assume you did.
I don't know what that is, so maybe not.
That's so interesting. You don't know what Powder Puff is. Maybe that's... I thought that was like kind of a national thing. So Powder Puff, at least at the high school that I was at in Utah, was when it was like a one-night thing where the girls would play football and the boys would be the cheerleaders.
Okay, I have never... Well, let me quantify that. I went to an all-male high school.
Oh,
so
that doesn't really work then.
It's possible that that's the reason I don't know what this is, but...
That's totally why. It doesn't work at all.
Yeah, I've never heard of it either way, so...
When I was in high school, Powder Puff was fun. I got to be an outside defensive linebacker, and I gotta say, it was just so much fun to plow into people like that. Like, just hit them straight on, tackle them, feel like you're tough. I don't know. I really loved that. Although, I will say, the next morning, I was incredibly sore. I could barely move. Because obviously, I wasn't conditioned for this.
Yeah, I remember even when I was in middle school, actually, I broke my foot playing basketball. So I know what you mean by the next morning, like, it feels like you've been...
run over by a truck.
Yeah.
But I mean, regardless of if we're big football fans or not, I mean, I think it doesn't take a genius to notice that the NFL is a multi-billion-dollar industry. In fact, the NFL has continued to grow their year-over-year revenue all the way up to $15.26 billion in 2019. And then they dropped to $12.2 billion in 2020 because, a global pandemic.
Mm-hmm.
But even in a year with a global pandemic, the NFL still made $12.2 billion. And that is insane to me. It just shows how big they are. In fact, the NFL is the most profitable professional sports league in the United States, with around 100 million people, like you, Ernest, watching each Super Bowl alone.
Right. And mind you, I don't really even watch it for the game per se, but it's just because it's usually friends will have, their Super Bowl parties and everybody's having fun and eating barbecue and whatnot. So that's really why I go.
I watch more for the commercials these days.
Pretty much. It's all about the ads and the halftime show.
Exactly. But that brings me to my next question.
Okay, what is it?
Are you familiar with the name Mike Webster?
Unless he happened to be the gentleman who founded the dictionary. No, I do not know who Mike Webster is.
Dictionary, nice. No, it is not that Webster, unfortunately. So many of our listeners are probably familiar with this story, but then many of them probably are not. But as a refresher, or to inform those who don't know this story, Mike Webster basically played center in the NFL from 1974 to 1990, and he's considered to be one of the greatest centers in NFL history. He's got multiple Super Bowl wins, and he's been inducted into the Pro Football Hall of Fame. And for Steelers fans, especially, Iron Mike, as they called him, was completely legendary.
The object of the National Football League is to be the best, the Super Bowl champions.
Yeah, I have no idea who he is, but I know that is one of the most difficult positions to play in football on the offensive line.
Yes, it really is. And we're going to get into that because it plays into this story quite a bit. So after 16 years or so of playing for the NFL, Mike retired from football at the age of 38, which makes me feel so old.
Me too.
I'll be honest.
Me too.
Retired at the age of 38. So he retires at 38, and then instead of taking his pile of NFL earnings and then enjoying this relaxing retirement with his family, Mike basically started to lose it mentally. Even at the time of his retirement, when he was 38 years old, he already had signs of things like amnesia and dementia, depression, and he showed some really unusual behavior, eventually even choosing to live out of his pickup truck, okay? And this is a guy with a lot of money from being a huge football legend, right?
Mm-hmm.
And he developed a number of addictions and these weird, erratic behaviors. For one thing, he would actually tase himself in the leg to knock himself out so that he could go to sleep. And his teeth would start to fall out and he would super glue the teeth back in. So, to put it lightly, in these years immediately after his retirement, you could say the former football hero had really fallen from grace.
Yeah, that's to put it lightly for sure. Don't get me wrong. The majority of pro athletes go bankrupt within 4 years of getting out of the whatever organization they were, but this is not for that reason.
This is a little bit more extreme, for sure. So he's fallen from grace, he's exhibiting these erratic behaviors, and then in the year 2002, at the age of 50, Mike unfortunately had a heart attack and he died.
The Pittsburgh Steelers' Mike Webster won 4 Super Bowls, famous, wealthy, revered. He died homeless, broke, and alone.
Mike Webster died today. A heart attack took his life at the age of 50.
And that may have been the end of his story, except there was one man in particular who was on duty at the Pittsburgh morgue the day that Mike's body was brought in.
The heart attack cannot explain his life after football.
The man's name was Dr. Bennett Omalu. He was a Nigerian-American physician, forensic pathologist, and neuropathologist who was tasked with conducting Mike Webster's autopsy. And Dr. Omalu didn't know anything about football, right? He had never heard of Mike Webster. They didn't have the NFL where he grew up. But he could see by the broken state of Mike's body that the man had clearly suffered from some kind of significant mental decline, right? And even though a heart attack was what officially killed him, Dr. Omalu couldn't help but wonder what in the world had caused a Hall of Fame football great to mentally deteriorate in this kind of a way. So he took a look at Mike's brain, but simply looking at it from the outside, it appeared completely normal. It wasn't shriveled up or misshapen or something like that as one might have imagined, given the state of mental decline he was clearly in. And most people in Dr. Omalu's shoes would have probably stopped there and simply written the cause of death as being due to his heart attack and then moved on to the next case. But Dr. Omalu still had questions he couldn't shake from his mind, so he arranged to have Mike Webster's brain tested further, paying thousands of dollars for the tests out of his own pocket, which I think is super interesting.
Yeah.
And these tests revealed something that Dr. Amalu had never seen before. There were these large accumulations of what's called tau protein, and they had spread throughout Mike's brain and then clumped together in areas that affect things like mood, memory, and behavior. And I mean, put simply for the layperson like me, it was like sludge basically spreading and choking out those specific sections of the brain. And that was honestly something Dr. Amalu had never seen before. So together with colleagues in the Department of Pathology at the University of Pittsburgh, not too far away, Dr. Amalu published his findings in the scientific journal called Neurosurgery, and then he gave Mike Webster's condition a name: chronic traumatic encephalopathy.
CTE.
Exactly. A degenerative brain disease somewhat similar to Alzheimer's in many ways, but it's triggered by repetitive trauma to the head. And not just concussion-level trauma, but subconcussive hits to the head as well that players, just regularly shake off and deal with. We're talking about the everyday hits that a football player receives during every practice and every game. For some reason, these repetitive hits to the head appear to cause this tau protein to basically branch out and attack these specific brain functions. And symptoms which don't set in until after years of repetitive head hits, they include things like mood and behavioral changes, aggression, violence, depression, memory loss, and eventually can turn into dementia until the person just can't do normal daily tasks on their own.
Two-time Super Bowl champion Leonard Marshall.
I just noticed that my behavior was starting to change. My patience or lack of patience was starting to diminish. I would forget things, forget financial responsibilities, take things for granted, short fuse with my daughter, short fuse with my ex, indecisive.
A normally pleasant and loving father can quickly become paranoid and aggressive with their family members. Many fall into addiction and die young. Even more commit suicide to escape their degenerating mind. Family members are left behind, broken, and completely confused.
Yeah, that's true. All you have to do is look at a lot of the, news headlines that have happened over the last 10 years or so, where you have a bunch of NFL players that commit crimes after their time, but some even while they're still in the NFL, even going so far as committing murder.
Yep.
And then you have to wonder, why does someone who fundamentally has a great position in life do something like that? And it's because it's not normal.
Right. And we hear the headlines all the time. And for years and years, I think we were all just like, man, they hire a bunch of irresponsible butts to work in the NFL because they're doing all this stupid, irresponsible stuff. But it turns out that maybe there's more to this than that. You know what I mean? Maybe it's not just people are irresponsible. Maybe they're actually going through something physically in their minds that's driving them in these different directions. And we could spend a long time talking about that. But I think the key is that there's a problem here and we're just starting to scratch the surface, right?
Mm-hmm.
So in Mike Webster's case, like you were talking about earlier, Ernest, playing center throughout his career, he was in prime placement for these repetitive hits to the head. That's a rough spot to be when you're playing football.
Mm-hmm.
And it wasn't just in his 16-year NFL career, but also playing football in college and in high school. Put together, Mike had been repetitively hit in the head over more than 25 years of football. And according to doctors, this was the equivalent of being in 25,000 car crashes. They said it's kind of like driving 30 miles per hour into a brick wall. Even these simple, small hits were that extreme.
Yep. A human body is just not designed for that.
Right. But then as you might imagine, with Dr. Amalu's paper being published only 16 or 17 years ago, there is still a lot that we don't know about this CTE condition today. And one of the main reasons we don't know much is that CTE can't yet be diagnosed in a living person. The only way to really know if a person has CTE is to actually cut up their brain and then look inside it, which is obviously a little hard to do to a living person. And CTE can't be detected in any modern medical testing on a living human being. You can't just run a CAT scan on them or an MRI or something and find signs of CTE. It just doesn't work like that. Although scientists are working on trying to diagnose it in a living person at this very moment, that's something they want to be able to do.
I was about to ask you that when you started delving into the whole CAT scan and MRI. Those are pretty advanced procedures. And I know at least with CAT scans that you would think that being that this is a protein, they'd be able to
see it.
Maybe inject you with something that would bind to the protein and glow or something like that. But
yeah, my naive mind thinks the exact same way. I was like, how do they not see this? Can't you just do the glow test,
And Jolie, that's why we are not doctors.
Right. But now, hundreds of brains have actually been dissected and studied since Mike Webster's death, and it's clear at this point that there is a factor that many of these brains had in common. They were football players.
There was a study that was released by the researchers with Boston University that looked at the brains of 202 deceased former football players, and they found evidence of CTE in 177 out of the 202 players that they examined.
That's our engineer of the day, who we'll introduce in a moment.
And they found CTE in the brains of these deceased players at every level of play, all the way down through high school. Where at the NFL, they found CTE in 110 of the 111 brains that they were looking at.
Isn't that crazy? CTE was found in 110 out of the 111 NFL player brains in this study, which is an undeniable correlation.
I'm sorry, but when it's 1 out of 111,
it's like all except one. It's like who's the guy who sat on the bench like his entire life?
Yeah, that's less than 1%. So right, either it's who's the guy that sat on the bench the whole time, or what about his physiology or whatever makes him different that he didn't develop this.
Yeah, that's a really good point.
Because that could help to understand, how to prevent it.
A devastating blow to the NFL. 99% of deceased players' brains examined in a new study showed signs of CTE.
This is much more common in football players than we previously anticipated.
Originally, they only had Mike Webster's brain to look at, right? Dr. Omalu had seen this first in Mike's brain. And then eventually a few others started to pass away from like suicides or like really reckless behavior. And they looked at these brains and they found CTE in them as well. And they were NFL football players. And so when the information was first just coming out of Mike's brain and a few others, you can imagine how the NFL took this news when Dr. Omalu first released his paper.
Yeah, I would imagine it's the same way that the tobacco industry took the news, or the pesticide industry with DDT.
And it's interesting that you should compare the reaction of the NFL to the tobacco industry, because that's exactly what Congress accuses them of, which we'll talk about in a little bit here. And I won't go into too much detail on the NFL's reaction because I do want to get into some computational engineering. But I will say that the NFL initially dismissed and denied that CTE was linked to playing football, even going so far as to ask Dr. Omalu to retract his paper, which is something that people just don't do. You don't ask somebody to retract a scientific paper. And Dr. Omalu didn't do it. He refused. And the NFL then held their position, even among increasing evidence, until basically Congress, as I mentioned, dragged him into a hearing and accused them of being like the tobacco companies, knowing cigarettes caused cancer, but then telling everyone the opposite.
And the medical experts should be the one to be able to continue that debate.
The NFL sort of reminds me of the tobacco companies pre-90s when they kept saying, oh, there's no link between smoking and damage to your health.
So since then, the NFL has changed their tune a bit, and they're working to make the sport safer. Because I think the evidence is pretty undeniable at this point. They've been a little strong-armed into that, although there is still much work to be done, right? In fact, for anyone who wants to learn more about this story, you can actually watch the Will Smith movie called Concussion, which I watched a couple weeks ago.
I found a disease that no one has ever seen. Repetitive head trauma chokes the brain.
The NFL does not want to talk to you. You turned on the lights and gave their biggest boogeyman a name.
And it, for the most part, actually seems to be a pretty accurate portrayal of Dr. Omalu's discovery and the NFL's reaction. Will Smith plays Dr. Omalu, and it's really interesting to watch. Have you seen that, Ernest?
No, like I said, I'm not really a fan of Will Smith's acting.
That's right. Because of Fresh Prince of Bel-Air.
Yeah, I mean, every now and then I'll, watch one here and there, but it's just, yeah. I'm sorry, but he will always be the Fresh Prince.
Chilling out, maxing, relaxing, all cool and all shooting some b-ball outside of the school.
But there's also a really good frontline documentary called League of Denial, the NFL's concussion crisis.
There was this change in personality where he didn't trust anybody. He thought everybody was out to get him. That wasn't the Mike I knew and loved. That was the brain injuries.
I'm really wondering where this stops. I'm really wondering if every single football player doesn't have this.
They interview a lot of today's top researchers on the subject, and you can actually watch the full documentary online at pbs.org. So that's a really good place to go and learn more without, the Hollywood interpretation and creative liberties sprinkled in there, or the Fresh Prince of Bel-Air, if you can't handle that.
Yeah, without Uncle Phil's nephew telling you about it.
I put my Walkman on and said I might as well kick it.
But all of this brings us to our subject for this episode. Every single football player brain that has been diagnosed with CTE spent its football career inside of a human skull that was nestled inside a football helmet, right? The whole reason that we have football helmets is to protect the players' heads. But if damage in the brain is still extensive across football players in general, are these helmets even effective?
Helmets have been around for, over 100 years or so.
That's our engineer friend again, Tate Fonville, a research fellow studying for his PhD at Liberty University. And among Tate's many skills like disc golf and 3D printing, Tate has a unique expertise: football helmets. Tate says that the earliest form of football protection looked kind of like Santa Claus hats in the late 1800s, and then they eventually evolved into the old leather cap in the early 1900s that most of us have probably seen in pictures.
They came up with that because the players who were playing football would come away with cauliflower ear, which, if you know anything about wrestling or boxing or rugby, if you have repetitive impacts to the side of your head, like glancing blows, which the early days of football, it was very similar in style to rugby. And so these guys, they would come away with gnarled ears, cauliflower ears, what they'd call it. And so they said, okay, we need to improve our helmet technology to protect against cauliflower ears.
But the leather caps were prone to overheating, and frankly, they didn't really protect the head very well. So in the 1940s, these leather caps began to be replaced by plastic helmets that were thought to probably offer better protection and comfort.
Tackling in football makes defensive play effective. You must be able to tackle to win.
We added face masks because players were getting injured and their jaws were breaking. They're getting a lot of facial damage, and so they added in, actually they started with a kind of a clear polycarbonate, like a shield that was completely clear, which actually I think is super cool. I think it would be awesome if helmets went back to that, but at the time, you have this very brittle plastic material, and so, this thing that's supposed to protect your face, when you got hit in the face, now you have shards of sharp plastic coming at your face. So that didn't stick around for too long.
And while helmets existed to protect players' heads, they were considered more of like an optional convenience for a while. I mean, for instance, the NFL themselves didn't start requiring helmets until the mid-40s.
The irony is, like, you make it a requirement, right? Which is for a reason. And then when somebody tells you that this brain damage is a result of head trauma, they're like, no, that's not possible.
It's fine. It couldn't be. What?
That doesn't even add up. Like, you're making helmets a requirement. You actually fine players when they take their helmets off, right? When they're not supposed to. Mm-hmm. Clearly, there's a problem. So their argument didn't hold water, I guess, in front of Congress.
Helmet development with respect to saving lives and preventing concussions didn't really start until 1969. That was one of the most deadly years in American football. And if you weren't aware that people died playing football, they do, especially in the early days of professional football.
In those days of football, the equipment was pretty rudimentary, and the rules were also a lot looser.
And it is indeed more than a football game. It is a true extravaganza in every sense of the word.
I think the statistic was in 1969, there were 36 men in professional football who died from traumatic brain injury.
36 deaths in 1 year. And that was just from those where there was an obvious correlation between a head impact playing football and death. There were still others who died of things like spinal injuries and other problems altogether. And 36 head impact deaths just couldn't be ignored, right? So in 1970, the National Operating Committee on Standards for Athletic Equipment, or NOCSE for short, was founded with the goal of enforcing a new set of safety standards for helmets and also other athletic equipment.
Their first objective was, how do we develop a set of safety standards for football helmets to make football helmets safer for these players? And so they didn't publish their first safety standard until 1973, but that standard has been in place ever since 1973 and continues to be the standard for certifying a football helmet to go into play. So you can't purchase a helmet today, and since 1973, you can't purchase a football helmet unless it has this NOXI stamp of approval.
Yeah, and it doesn't surprise me that this really hasn't evolved much since 1973, because it's one of those things where people will always put the minimum amount of effort into something that they possibly can.
That's so pessimistic on human beings.
But you know it's true.
No, it probably is.
They will always put the minimum amount of effort into things. So this was enough to say we have a standard. As long as we meet that standard, we're fine. But the reality is standards need to evolve.
And NOXI kind of borrowed from the automotive industry when they were developing these standards, because the auto industry had seen a lot of traumatic head injuries that had resulted in fatalities.
The automotive industry was collecting data by dropping these human cadavers down elevator shafts with pressure gauges screwed into the skull.
Which, yikes.
So they would drop these cadavers at varying heights, and when the cadaver experienced a skull fracture, then they recorded the pressure and calculated the peak G value. And they developed what's called the Wayne State Tolerance Curve, and that was back in the 60s. And so NOXI, when they were looking at, well, how do we design something to protect the head, they looked at that data and said, okay, let's set our standards on skull fracture. And they used the G levels that were produced from those studies as they're certifying. So all helmets that met the NOXI standard basically should prevent skull fracture. And the assumption was skull fracture equals death.
Which, I mean, you can see where the issue here was, right? Back then, they were going off this assumption that skull fractures were the deadly head injury to focus on. And today, we know that it's not just skull fractures that we need to be worrying about, not even concussions, but repetitive subconcussive impacts are thought to also lead to CTE.
And the standards have just slightly modified since then, and only within the past couple of years did they add another metric in there to kind of measure the rotational accelerations that are going on inside the head. But apart from that, the football helmets that you see on the field today, they have to pass that certification, so that if you're wearing that helmet, you shouldn't be getting skull fracture and dying from blunt trauma to the head.
But you could still get a concussion or less, which could add up to more.
So if you're wearing a football helmet and you're expecting it to protect you against concussion, but it was designed to protect you against skull fracture, then you may find that you're still going to have these lifelong debilitating consequences of repetitive head impacts, because that's just not what the football helmets, at least historically, have been designed to prevent against.
It wasn't until the late 90s and early 2000s that people started to consider designing helmets to prevent against concussions and not just against skull fractures.
People in the NFL were starting to experience a large number of concussions, and there was an investigation that was going on about the correlation between impacts in football and concussion.
And then it began the push and pull between scientists and the NFL, with some, like Dr. Amalu, saying that repetitive hits to the head caused long-term damage, and others, like those associated with the NFL, especially for those first few years, denying any correlation. But more and more football players were dying, their brains were being examined, and eventually the NFL couldn't deny that correlation anymore.
It wasn't until 2009, when people started really studying concussion and CTE, that we found actually evidence of CTE in a football player who actually never had a reported concussion.
First, they were worried about skull fractures, then concussions, and now this.
So then designing football helmets to just protect against concussion is not even enough at this point. Now we need football helmets that can protect against kind of this unknown threat, this accumulation of concussive and subconcussive level impacts throughout the whole life cycle or the career of a player.
And this is where Tate comes in, or more specifically first, his advisor, Dr. Mark Horstmeyer, now Dean of the School of Engineering at Liberty University. In the early 2000s, Dr. Horstmeyer was an engineer and a researcher for thermonuclear weapons, where he helped develop some very advanced and accurate material computational models for metals.
It's basically this notion that you can start at the atomistic level, and you can start to understand, based off the material or the compounds that you're working with, how do these different atoms respond to one another, and building models that correlate your behavior from the atomistic length scale all the way up through the different length scales, and how the microstructure affects the performance all the way up to the continuum level, where you're able to run simulations at the continuum scale. That's kind of the visible length scale that we work in, that we live in. And you can have very accurate descriptions of how materials behave because you have linked all these lower length scale phenomenon, and you're able to track the history of the material.
Which, I mean, since I almost majored in thermonuclear weapons engineering and I totally understood all of that, Ernest, maybe you could help interpret for anyone out there, you know, some of our listeners who may not have understood.
Essentially what they're trying to do is look at things from the atomic level, right? And then see how the compounds operate at that level and then try to build models, right, from that. It seems almost like a false hope, though, because even if you manage to get the helmet to absorb the most that it possibly could, right, you're still dealing with the fact that you have two bodies of a given mass and a given velocity that are going to run into each other, and the brain is going to move, right, or be impacted inside of the skull. So
you're of the opinion that basically football should be illegal.
No, I look, I'm one of those people that says, do what you want to do. That's your business.
Right, yeah, but know the risks.
It could be possible that in the future we come up with some kind of magic material that is able to absorb 100% of the impact, but it just seems like it's not possible.
Like even if you had the most amazing helmet created from the best materials available on the earth that give you the best results, it still wouldn't result in 100% of absorbing the impact.
Let's say hypothetically you got the helmets to absorb 100% of the energy from the impact. That's great. That stops the immediate blunt force trauma to the head, but you still have the bodies and their mass moving at a certain speed. And then, you know, the head is attached to the body via the neck. So somewhere that energy is going to get displaced that's for the mass of the rest of the body, not just the head. So short of like, I don't know, some kind of full body suit that absorbs all impact and just
Iron Man
sets you to net zero, I just don't see a solution to this problem.
Do you think that it's worth pursuing so that football helmets can be made safer to maybe mitigate?
Oh, absolutely. I think it's absolutely worth pursuing, and they should try to make the best that they can possibly make to try to minimize the long-term damage. I'm not saying to just give up.
Right.
But what I'm saying is I don't think this problem is actually solvable. You can,
as far as like 100%?
Right, 100%. You can do better and better and better, which I'm an advocate for, right? To try to help these people. But yeah, I don't see it like a perfect solution or a permanent solution to the problem.
Right. And then it's a matter of discussion of how good can we make the helmets so that how much damage can we minimize? And then what is the exact risk? How do we communicate that to those who actually play football so that they understand what the risk is and they weigh that risk? Because, I mean, remember, the NFL is a $15+ billion industry per year, or at least it has been in 2019, and it's been pretty close before that as well. I don't see people letting go of that.
No, they're not going to let go of it. And then you also have to consider this. If I owned a $15 billion a year sports organization, and I knew, even if I didn't acknowledge it publicly, that traumatic brain injury was coming as a result of this, and I thought there was a materials science solution to that problem so that I could keep my $15 billion empire running, I would fund an unlimited amount of research into this to solve the problem.
Right.
The only way I wouldn't fund it is if I knew the problem couldn't be solved.
But you're saying it can't be.
That is my perspective on it. I'm not trying to accuse the NFL of doing anything here because I don't want them coming after me. But I'm just saying,
you don't want NFL lawyers banging down your door?
I don't want NFL lawyers.
They're easy to fight.
I don't want them bothering me. But what I'm saying is, as far as I'm concerned, it's unsolvable, but you never know. Every problem that has existed in the history of our species has been unsolvable until it was.
You know what? That's a really good way of putting it. And it is exactly what Tate and his team are working on.
That's when Dr. Mark got involved and said, hey, I can use this modeling paradigm to model biomaterials, and we can actually design helmets that better protect the brain.
He could potentially translate his background in computational modeling for thermonuclear weapons into understanding how head impacts affect the brain. So first, he started by studying various animals that get hit in the head a lot, but don't seem to suffer any damage from these head hits. Animals like bighorn sheep and woodpeckers, or even some bison and fish. I mean, what allows them to knock heads over and over and over again without their brains deteriorating?
So if you can kind of develop a model for biomaterials and for brains, and then you can use the simulations to reproduce their impacts, then you can understand what's going on inside of these animals' brains. And you can kind of use this same modeling paradigm to look at their different features, the horns or the bones that they use, the structures in their skull, how they utilize these different features to actually protect their brains.
And I think this is crazy interesting. So for instance, think of our human brains. They're basically just floating in fluid inside of our skull without any kind of real cushion between our brain and our skull. So if we get hit in the head or if we experience whiplash or something, our brain can simply smash into our skull, which is not so good for the brain, obviously. But take an animal like the woodpecker, for instance. Woodpeckers are constantly banging their heads against hard surfaces. It's part of who they are. So how are they able to do that without constant brain injury? Well, it turns out that a woodpecker has a long tongue that not only sticks out of the mouth, but it goes back into the head and it wraps around the bird's brain, holding it in place and acting as a sort of protection, preventing the brain from banging against the skull. I mean, how crazy cool is that? If only we all had these epically long tongues that could wrap around our brains. But I mean, now that I say that, I'm like picturing some kind of creepy lizard people, and I don't think I want that.
Yeah, this podcast has just jumped the shark. We've now talked about the lizard people on it.
From supersonic jets to personalized medicine, industry leaders are turning to Rescale to power science and engineering breakthroughs. Rescale is a full-stack automation solution for hybrid cloud that helps IT and HPC leaders deliver intelligent computing as a service and enables the enterprise transformation to digital R&D. As a proud sponsor of the Big Compute podcast, Rescale would especially like to say thank you to all the scientists and engineers out there who are working to make a difference for all of us. Rescale, intelligent computing for digital R&D. Learn more at rescale.com/BC podcast.
I was about to say, I would think, right, the reason that some of these animals are able to have this happen without becoming chronically injured is because they have anatomical things prevent them. I understand the premise here that we're looking at kind of the material science, the bio aspect of this to see how these atoms react with each other. But I look at it in the bigger picture, which is there are evolutionary things that happen here. There are anatomical changes to these creatures that allow them to do that. And so because humans were not designed for this kind of thing, and because the percentage of the population that undergoes these type of things is so small, I don't see there being a human evolutionary step to have an anatomical way to stop this.
Right. And I think that that's what Dr. Horstmeyer was thinking as well, is let's look at this evolutionary anatomical way that these animals are able to not get, concussions and brain damage from these repetitive head hits. And let's see if we can duplicate that in kind of an external way, right? So we can't obviously modify the body, but maybe we can duplicate some of what we can see in nature in like a football helmet or something.
The woodpecker was a big one where they were looking at, and they were able to model impacts and study how this impact correlated to pressures and stresses and strains within the brain.
Sometime around 2009, Dr. Horstmeyer and his team started looking at pig brains, which have a lot of similarities with human brains, which you can take that however you want to take that.
We had a pig farm nearby. We had a partnership with a guy who would donate fresh pig brain. I'm very thankful I was not involved with that research.
Could you imagine like how they kind of sparked up that relationship? Like someone walked down the street to the neighbor and said, "So I see that you have pigs and I'm in need of pig brains. Can we work something out here?"
We had a test apparatus that's able to test high and low velocity strain rates or high and low strain rates of these different materials. And we were able to do these experiments and then use this modeling paradigm to actually calibrate a model to brain.
And it appeared to be working.
We used this model in a lot of our finite element calculations. And we were able to start running simulations on head impact and doing head trauma studies.
One of the earlier studies they worked on in this way involved a military soldier who had been near a bomb that had detonated nearby.
And the pressure wave went through their head and they got a concussion. And we were able to reproduce that and actually show with our model that we came up with the same result. And that was kind of the first big thing with our brain modeling, was we were able to use this hierarchical multi-scale internal state variable model to reproduce real-world phenomenon.
So in the early 2010s, Dr. Horstmeyer's team began applying all of this to football helmet impacts and began looking at things like performance of helmet liners, optimizing the face mask, and other elements.
They were actually able to really improve these helmet designs. In one case with the helmet liner, they were able to reduce the peak G values of the head and reduce the likelihood of concussion down to about a 25% level, which is about a 50% reduction. And then with our face mask optimization, they were able to look at tensile pressures and shear strains in the brain, and they were able to see a significant improvement over a baseline face mask.
And it's at this point that Tate jumped into the game.
I'm continuing this vein of developing good models of the brain, good physics-based multi-scale models of the brain that we can then use in these high-performance computing, these finite element analysis calculations of impact on the head and helmet, and then we can actually directly try to correlate impact conditions of various types to how the helmet responds, and then how that helmet transmits energy and stress waves to the head and the brain. And we can use this model to really study how the brain responds and deforms under these impacts.
And while other researchers have used finite element calculations to study how impacts to the head actually affect the brain, they're very limited in their modeling capabilities and can only really see simple stresses and strains that can be correlated to on-field concussive data. And it basically just tells them a certain likelihood of a concussion. But Tate's research is different.
We're able to use this model that we have, this physics-based multi-scale model of the brain, and we're able to actually study, we're actually able to directly quantify damage and damage growth in the brain.
Yeah, this is interesting because I think this kind of hints toward, if you're going to solve this problem and if it's solvable, right, you have to work backwards from the actual damage being done. Trying to do it from the outside has gotten us so far. I'm not going to try to negate what's been done already, but it'll only get you so far, right? Mm-hmm. In order to actually solve it, you have to say, okay, for example, the tau protein calcification around these specific points, this is what is the ultimate result of this problem, of this traumatic brain injury. So how do we prevent that from happening? And the only way to do that is to start from the injury backwards.
Yes, I totally agree with you. And without simulation, or even with limited simulation, helmet designers basically put together prototypes and then they impact test them to see how well they worked, working from the outside in, exactly like you're talking about, right? But with Tate's research, by using computational simulation on these models that they have, they can design football helmets, like you're saying, from the injury out. So like from the inside out.
I'm a huge design nerd. I love to design, build, test, that kind of thing. But in parallel to that, I've been able to dive into the physics of the brain and how the brain responds to different impacts and develop this model and calibrate this model to the brain. And I'm able to actually use this model to directly quantify damage in the brain when we run an impact simulation.
Tate's team can run a simulation of a head impact where the head is basically wearing a football helmet made with certain materials assembled in a specific way, and then they can actually quantify what the damage in the brain would be. In a way, they can foresee the unseeable.
That's awesome, because that's really, again, that's kind of the bread and butter of this. If they can reliably show in their models how this impact is translating to damage, and they're able to negate that, then they will have a better solution than anyone else has.
Right. And right now, they're focused on a specific part of the football helmet that could make the biggest difference.
We are looking primarily at the foam, or the liner, basically what stands in between an impact and the head. And we're looking at novel ways to design that foam liner such that it traps the impact momentum, it dissipates the stress wave, and it absorbs the energy.
Remember, traditionally, football helmets have been designed to protect against skull fractures by primarily absorbing impact energy.
Then you have this other design paradigm that we're kind of bringing to the table that says we can use computational engineering and high-performance computing to study what's going on in the brain, and now we can design helmet systems that don't necessarily dissipate impact energy as our primary objective.
By using high-performance computing, Tate has a significant advantage over traditional helmet designers who instead look at the kinematics model that can really only show them the likeliness of a concussion or external damage. I mean, think about it. What if what we've always assumed about head damage is completely incorrect? I mean, what if the impacts that appear to do the most external damage to the head actually don't do as much internal damage to the brain, and instead it's some of the lesser damage culprits to the head that are actually impacting the brain the most, like whiplash or something? I mean, I'm not sure what the results are, but if we can assess damage to the brain instead of just observing the effect on the outside of a head, I mean, how much more accurately can we start to know what protective headgear is the most effective?
Yeah, exactly. Because I think at this point, the overall goal is to limit the amount of movement of the brain inside the skull.
Mm-hmm.
Right? If the brain moves less, it's less likely to have an impact with the skull, or it's less likely to be jostled.
Mm-hmm.
So that's what they have to do. And like you said, maybe the foam is great at stopping, a skull fracture or a concussion or something like that, but it's not functionally limiting the actual movement of the brain inside the skull.
We're able to look at our different helmet iterations in this computational environment, and we're able to look at the damage that grows in the brain as a result of an impact. And so instead of looking at stresses and strains and how they correlate to the probability of a concussion, we look at the actual explicit damage growth in the brain. And at the same time, we have to be able to build a helmet that is good for trapping the impact momentum, dissipating the energy, and kind of mitigating the stress waves. We have to be able to design a helmet that does well there and performs well in their tests, right? We have to have a NOXI certified football helmet, which actually isn't that hard to do. But we have to have a test that also performs well with their metrics. And we want to be able to show with our computational work that this helmet also minimizes damage in the brain, which I don't think any other helmet innovator at this time is able to do.
They still run physical tests on an actual prototype, but they just start with computational simulation.
We'll use the computational resources to iterate through hundreds or thousands of options of helmet designs, and we'll pick the one that minimizes brain damage and maximizes energy absorption. And then we'll build that helmet prototype and we'll take it out to our lab out here at Liberty, and we'll test it. And we'll use the exact same boundary conditions that we were using in the computational environment that we use in the test. And those are the same boundary conditions that all these different agencies, like the guys at Virginia Tech or the guys with the NFL or NOXI or whoever else, they've put forth this set of test metrics that's supposed to sort of emulate or replicate the impacts that you actually see on the field. And we put our helmet through that same test method because at the end of the day, we still need a helmet that does well in the metrics that the industry understands.
Because remember, this kind of technology isn't yet utilized by those who create the football helmet safety standards.
We have what's called a drop tower, and this is something you're probably going to find in almost every helmet innovator shop out there. It's just twin rails. You have an aluminum drop carriage. It's kind of a configuration of aluminum tubes with a head that you can position in these different areas. And this is a adult male 50th percentile head form replica. You have an accelerometer that's embedded in the center of gravity of this head, and that's what is used for this NOXI test that certifies all the helmets. You can put it in 6 different orientations and you drop it from various heights just straight onto an anvil, and so it kind of drops and hits. And the acceleration time history is what they base their metrics on.
And then there's a second test they also run
called linear impactor, where that's a pneumatically driven impact device where you put a helmet on a head that has 9 accelerometers that's able to calculate both the CG, the translational center of gravity kinematics, but it can also measure the rotational metrics as well, which is something that just within the past 10, 15 years, the industry has started to identify as something that is highly correlated with concussions, is that rotational motion.
AKA whiplash.
That happens when you take a hit to the body, or when you get slammed to the ground, or, you hit somebody and your head glances off.
You use sort of a crash dummy head, which apparently costs like $15,000 or something. And even if your football helmet is awesome, if you run the test at full power, it can totally bust up your expensive head.
It really kind of sheds new light on what a player actually goes through in a concussion-causing impact.
Ouch. And it's important to go back and look at how football helmets are tested and evaluated without the computational models that Tate's team has. How are these safety standards created that are then given to helmet developers to measure against to know if they've made a good helmet, right? Well, first, you look at the plethora of angles of NFL video footage, which we have a lot of video footage this day, and you look at football players who have gotten concussions, and then you try to categorize and evaluate what happened during that concussion by watching all of these angles of video.
They kind of separate those out into all these different locations and directions and velocities, and they try and recreate those with their test dummies. And what they're doing there is they actually have these accelerometers embedded in the head of their test dummies, and now they're recreating an impact that caused a concussion in the game. And now they have this accelerometer time history that they can use to describe the kinematics of the head and the body and the torso and everything as a player's being concussed.
And then that data can be released to researchers who can run finite element calculations and basically take those accelerometer time histories and apply them to the head.
They're applying the boundary conditions to the skull of their head finite element model. And then they're able to see what's going on inside the brain. And then they take those values of stresses, strains, maximum principal strains, things like that, and they build those into models that are connected directly to the kinematics that are based on the likelihood of concussion. And now they can build a test in a laboratory environment that recreates the concussion-causing impacts and shows the likelihood of a concussion.
And while all of that is cool and helpful, a computational experimentalist can see the flaws that potentially lie in that process.
You can start to see how uncertainties and errors really start to propagate from one thing to another. So it all starts with, did that player actually receive a concussion? Well, we don't really even know what a concussion is. We can't really tell if, that player actually received a lower end of concussion or if they're really okay. And we also can't tell. You can't study everything, so you can't tell what subconcussive level impact actually is necessary to replicate to prevent against CTE. So the loss of information from one thing to another by simplifying, all from your observations to your reproductions, to your finite element calculations, to your metrics, to your laboratory test environment, that all results in the metrics that are driving helmet development today.
Instead, imagine if those people who are developing helmet safety standards were using computational simulation to not just determine injuries to the head based on impact, but how those injuries were actually affecting the brain, both in the short term as well as over time.
Yeah, I think what happened here is there's this kind of just basic assumption that the harder the impact, the higher probability of a concussion, which the correlation is probably true. But as Tate mentioned, there are a lot of other factors that play into this, and the science becomes imperfect when you're essentially taking a dummy and punching it from all these different angles. That's giving you like an outcome-based answer instead of one that is looking at the actual engineering and science behind the dissipation of energy from collision of mass.
Right. And I mean, they're doing a lot, I think, that it's still advantageous to have that kind of information. But I would wager that incorporating computational technology into this testing process would only enhance those efforts and maybe even direct them on a different path in some areas, is my guess.
So when somebody else wants to make a new football helmet, they buy a piece of test equipment, they make their prototype, and they put it through this test, and they say, oh, good, I got the highest score on this test, so therefore I must be the safest helmet. Well, yes, according to everything that kind of built up that assumption. But on the flip side, what we're doing is, kind of starting from the inside. We're saying we want a physics-based multi-scale model that can actually directly measure damage and its growth in the brain. And we want to skip all those steps and just look at optimizing a helmet that performs well with respect to damage growth in the brain. But then when we find that answer, then we can actually build it and put it through the same gamut of testing.
But as Tate and his team have run their own tests,
something that we're finding today, a helmet that does well on brain damage, a helmet that reduces the likelihood of brain damage, is not going to be your top performing helmet with the metrics that they've produced.
which means maybe the football helmets out there on the fields are not actually the best candidates to protect the players from developing CTE and other injuries.
I would say that that's the equivalent of saying water is wet. However, it took someone like Tate and his team to kind of prove that water was wet to these individuals, if you know what I'm saying. So it's great that he's doing this. And yes, computational engineering, right? HPC in the cloud are really the only way that you can do this in a cost-effective and holistic way.
Right. And I mean, back in 1973, when they developed the safety standards, when NOXI came up with those, obviously they didn't have that kind of access. But maybe now that we do have it, it's time to look back, take a closer look at how exactly these tests are being done.
I think we're a long way away from changing the metrics because there are so many question marks throughout this equation, right? We are just getting started.
And Tate still has a lot more work to do before he sees his work influencing one of the biggest industries in the world. I mean, they still have more papers and data to release to show what they've discovered before they can expect anyone to change.
We're trying to change the paradigm, of helmet development. We're trying to introduce this information that says, it's not just the best foam that performs the best in your test that is the foam you should select. In fact, some of those foams may do really poorly when it comes to brain damage.
In the meantime, they keep running their tests and iterating on a football helmet design that will best protect the brain. They've even started their own football helmet company called Genesis Helmets so that they can eventually offer these helmets for sale. And so far, their helmet designs are actually performing really well.
We bought the top 5 helmets from 2020, and we beat the best performing helmet by about 5%.
They've also participated in a number of NFL football safety equipment design challenges, which are these competitions where the NFL actually asks researchers and engineers to come up with the safest football equipment, and then they're rewarded with grant money to basically continue their research, which I think that's a great program. I think it's a great use of NFL resources. And Tate's team has done pretty well in those competitions. They've even walked away with some grant money on occasions. And while the NFL doesn't have the greatest history of accepting scientific data about CTE, I think the fact that they have competitions like this does show that they've changed their tune quite a bit, at least from the initial denial where they told Dr. Omalu to retract his paper. This is a different NFL than what I saw back then.
Yeah, getting hauled in front of Congress can have that effect on someone.
No, that's true. I mean, whether it was forced or voluntary, the change is there, right? And while Tate's team has already been successful, sometimes they do miss out on grant money because, frankly, again, the tests that determine the winners of these competitions don't incorporate the kind of data that Tate's team is looking at, just like the industry safety standards.
We are still seeing awesome things on our end that aren't recognized by the community yet. We're actually seeing great results with respect to minimizing the brain damage and therefore minimizing the likelihood of concussion with our designs. And those things just aren't quantifiable yet with the tests that are available. And so we're still moving forward full steam ahead.
And they're planning to go to market with their new Genesis football helmets in the next year or two, with other helmets for hockey, lacrosse, equestrian sports, and others in development as well. And of course, none of their work would be possible without one very important thing.
High performance computing.
He said that like the second grader who had their hand raised for 10 minutes and
That's
was
right.
so excited to say it.
Not only is the material model very complex, these physics-based multi-scale ISV models, it's a sequence of calculations that kind of take you through the kinematics, the kinetics, the thermodynamics, the physics of what's actually happening. And it's this very long, very expensive model to run. And we have to run that through every element that's in the brain. And so, of course, if you have a finite element calculation where you have a geometry for the brain and you want decent enough resolution, you're going to have thousands of elements.
And care to guess what they use for their high performance computing?
I'm going to go out on a limb here and assume that it's rescale.
What I tend to use is a core that they call carbon, And Carbon, that's 44 cores per node. And it takes about an hour 20 to run those calculations on average.
Whereas without high-performance computing,
with just a standard desktop, we're talking about a month and a half to run one of those calculations.
Yeah, that would make sense. And that's been the common thread through all of the, people that we've interviewed over the last couple of months, that the difference in speed for running these simulations and the time to get your results is just drastically reduced by using cloud high-performance computing.
And the cost is pretty cost efficient as well. I don't have any statistics in front of me on how much these things cost, but hour 20 2D calculations, they're just a couple of dollars to run with Rescale setup. So if you compare that to the cost of actually physically building a helmet prototype and testing it, one, it'll take you about 3 months to source the materials and put together one helmet prototype, and it'll cost you tens of thousands of dollars. You do that in a matter of days, for hundreds of dollars, so to speak, for the high-performance computing environment.
In fact, Liberty University doesn't have an on-premises high-performance computing cluster. So when they started up their engineering program a couple years ago, the only way they could get up and running was by using a cloud-based platform. And in the end, it turned out to work especially well for them because they also have a lot of online students who are now just able to log on and run their simulations from basically wherever they are in the world.
Yes, and as a matter of fact, eventually the entire industry is going to have to learn this lesson, right?
Right.
And I realize that this is one of those things that are kind of a sensitive topic, but while there will always be very specific use cases and edge cases where you need an on-premise solution, the vast majority of people out there, the vast majority of any of this can run in the cloud, and it can run in the cloud cheaper, more efficiently, faster, and just overall in a better way.
We have kind of a younger department, and we're trying to really push the envelope and do new things in a state-of-the-art manner. And so we went looking for cloud-based high-performance computing, and so we came up with Rescale.
Before coming to Liberty University for his PhD, Tate studied at Mississippi State, where they did have high-performance computing on premises, which was super useful. But at one point, Tate actually tried to submit a bunch of job requests at the same time to run in parallel for several days.
Yeah, I can imagine how that turned out.
And I dominated the entire department, and the entire cluster was dedicated to this kid, Tate Fonville, and they came and found me.
Apparently it was, discouraged to take up the university's entire cluster for some reason. So when he later was at Liberty University, he was hesitant to try running multiple jobs in parallel again because he didn't want to get in trouble.
I very timidly tried this parallel approach again with Rescale, and I mean, let me tell you, it's been the best thing ever. I submitted 9 calculations this morning, and I submitted them in 3 groups all at the same time because I knew kind of in total it would take about 6 hours to run 3 of these calculations back to back. So if I want results when I go into the office this afternoon, I just submit all 3 of those at the same time, and provided we have the right amount of licenses available on site, then they all run in parallel and I get to work, and I do other things, and then I go to work in the afternoon, and all of them are done about the same time. And that's wildly efficient.
Yeah, there's a big difference when you're paying for it and when you're not and you're sharing it, with a bunch of other people. The beautiful thing about cloud HPC is that, number one, you're paying for it. So there's none of this like, well, I'm trying to reserve resources on a shared cluster. And the second thing is you're not really competing or sharing with other people at the exact same time. The whole model of shared usage in the cloud is one where there should always be resources available whenever you need them. Granted, you have to pay for them. But again, the overall cost to do this is just much, much less, and the impact to other users is negligent if it even exists.
And then for an engineer, like from an engineering perspective, Tate says that the process has been really helpful because he hasn't had to become an IT expert.
It makes sense.
I'm not great with code. I'm not great with understanding computer architectures and optimizing workflows for particular computer setups. And so when I first got started with high performance computing, there was a lot of guesswork. And there were a lot of trips down the hallway to the resident expert to say, hey, can you check my code? It got kicked out.
And Tate learned a lot along the way, but there was a lot of banging his head against the wall trying to figure things out.
Largely what cloud-based has done to alleviate that stress is they sort of make it this drag and drop environment where They kind of make sure that you have all your boxes checked, that the command script writing is largely provided for you, and they have a good documentation that can help you troubleshoot errors.
And once again, I'm sure our presenting sponsor will be happy to hear all of this.
Oh, absolutely. I would imagine that they would say, this is exactly why we exist.
The environment is so much more user-friendly and so much more easy to understand than what I was previously working with on-site computing.
And most importantly, this cloud-based high-performance computing technology is working to solve a critical problem. How do we better protect the hundreds of thousands of football players in the world against head injuries like CTE? And the key to this could lie in quantifying damage in the brain.
I see a lot of inefficiencies in football helmets today. They're heavy, they're bulky, they're huge. And I think that we can be more efficient with the materials that we're using if we have a better understanding of how those materials are responding to the impact and how those impacts translate to brain damage. So I would hope that as a result of my research, the community is able to better understand that connectivity between an impact and brain damage and the material in between, and they're able to make minimalistic football helmets, so to speak, that are exponentially more protective than what we have on the market today.
And today, researchers are innovating in ways they haven't before in a world of sports safety, from customizing foams to fit specific heads to rethinking equipment placement and design according to the football player's position.
There is a lot of room for innovation in the football helmet industry. And even when you take this technology and you apply it to other realms, like any of the snow sports or any of the board or cycling sports or the equestrian realm that use these helmets that have this kind of antiquated, expanded polystyrene foam that's what we call crushable foam. It's really stiff brick foam. I just see wild improvement that it's an untapped market of innovation that I hope that we can take our technology and apply it in those realms and drastically improve the safety of those sports as well.
To learn more about Tate and his work, you can follow Liberty University's publications, which we'll link to in the episode notes on bigcompute.org. And keep an eye out for Genesis helmets in the next couple of years. If you have a football player in the family, be it high school or peewee or pro or whatever, they might want to consider strapping on one of these babies to minimize damage in the brain, because remember, that's exactly how these helmets will be optimized.
Yeah, and I have a feeling we haven't heard the last from Tate and his team either.
Mm-hmm.
And to help share Tate's story and spread the word of the Big Compute podcast, please leave us a 5-star review on Apple Podcasts.
Okay, so you know how I've been, obviously annoyed with you specifically calling out only Apple Podcasts and kind of ignoring Spotify and Google Podcasts?
Yes.
So I just recently realized yesterday that you can't actually leave a rating or review on Google Podcasts or Spotify. The ability doesn't even exist.
Color me surprised.
So I would say that I owe you an apology, except for some reason I just can't find the words. But I did think that was super interesting because I've been telling people to leave us a review where they can't even do that. So
fail.
Or even easier, you could tell a friend, Slack a coworker, send a WhatsApp to a family member, tweet the NFL.
Oh, now they're really going to come after me. Someone there is going to hear this thing and be like, this guy. To which I will say, do better. Yep. So thanks for joining us. And don't forget to practice 3-2-1 backup and always use MFA.
Stay safe out there. Don't get hit in the head.